morning, I am Benedict Kawi, and today we will be talking about the three basic gas laws. So what are the three basic gas laws that we have? We have the Boyle's Law, the Charles Law, and the Gay-lussac Law. Now, let's begin. The first gas law is the Boyle's Law. The question is, at 1.80 atmospheric pressure, a sample of gas takes up 4.75 liters. If the pressure on the gas is increased to 2.50 atmospheres, what will the new volume be? First, we have the Boyle's Law. What we know about the Boyle's Law is that it has two variables, pressure and volume, and that they are inversely proportional with each other. So now let's solve. We are given with pressure 1.80 atmospheric pressure, and with its corresponding volume, which is 4.75 liters. Next, pressure 2, which is 2.50 atmospheric pressure, and volume 2 is unknown. So, to solve this, we use the formula P1 V1 is equal to P2 V2. We cancel P2 on this side so that we can isolate V2. Next, we are left with this formula. Now, to the solution. Just substitute the values that we have here, and this is your answer. The volume is equal to 3.42 liters. The next question is the Charles Law. A balloon takes up 635 liters at 0 degrees Celsius. If it is heated to 70 degrees Celsius, what will its new volume be? So in Charles Law, from what we learned earlier, has two variables, the volume and the temperature, and that they are directly proportional with each other. In the Charles Law, pressure is constant. And another thing to know about the Charles Law, or in any gas laws, is that when we use temperature, it is in Kelvin. It's because the Kelvin scale is used in gas law problems because the pressure and volume of a gas depend on the kinetic energy or motion of the particles. So let us begin with the problem. We are given with the initial volume of 635 liters and a temperature of 0 Celsius. And we have to convert the 0 Celsius into Kelvin. So just add 273. So the outcome is 273 Kelvin. Next, the temperature 2 is now 70 degrees Celsius. Just add 273 to get the Kelvin scale. So now it's 343 Kelvin. Volume 2, or the final volume, is unknown. So this is what we will be looking for. The formula that we will be using for the Charles Law is represented by this. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. Cancel both sides with temperature 2 just to isolate volume 2. Now, the outcome is this formula right here. In the solution, just substitute the values. Then, here's the answer. Last but not the least, we have the Gay-lussac Law. Now, let's read the question. The pressure in a sealed can of a gas is 245 kilopascals when it sits at the room temperature of 25 degrees Celsius. If the can is warmed to 49 degrees Celsius, what will the new pressure inside the can be? Gay-lussac Law, it has two variables, pressure and temperature. And these two variables are directly proportional to each other. So let's start. With the given, we have the initial pressure, which is 245 kilopascals, and the initial temperature, which is 20 degrees Celsius. But same concept with the Charles Law, we convert the Celsius to Kelvin. So just add 273 to 20 degrees Celsius. Here we have 293 Kelvin. Next, for temperature 2, the final temperature, it is 49 degrees Celsius. Just add 273, and here we have it, 322 Kelvin. So what we are looking for is pressure 2, or the final pressure. Next, we have the formula. In the formula, it's just P1 over T1 is equal to P2 over T2. Because we are looking for P2, we divide both sides, multiply rather, both sides by T2 so that we can isolate T2 in one side. Next, the solution. So, based on our formula, we just substitute the given to the formula. So, here it is. 245 kilopascals times 322 Kelvin, you do the math. So, I'm not good in math. So, here is the end. The final answer. 269 kilopascals. In scuba diving, divers have to be mindful of their breathing. Thus, they are taught to exhale steadily as they rise to the surface. because air is compressed when they are submerged. On the other hand, the air expands as they rise. Failing to release the air could lead to severe internal injuries due to the difference in pressure. Increasing depth leads to increase in pressure and decrease in volume. This inverse relationship between pressure and volume is exemplified in Boyle's law. When you buy packaged food in 7-Eleven, they usually open the containers a bit before heating them in the microwave. This is because the increased temperature causes the container to expand and increase in volume. The Charles law states that volume and temperature are directly proportional to each other. This is why we avoid heating plastics at intense temperatures. Gay-lussacs. At noon, a man leaves an aerosol spray can outside on the sidewalk. It stays under direct heat of the sun for at least a few hours. When he comes back, he notices that the can has exploded. This phenomenon is explained by the Gay-Lussac's law, which states that pressure is directly proportional to temperature. This is why people are cautioned not to expose aerosol spray cans to direct and extreme heat.
Marshmallow. The marshmallow in the syringe expanded when the plunger was pulled up and shrank when the plunger was pushed down. This was due to Boyle's law. The plunger being pulled up caused the pressure to decrease, causing the marshmallow's volume to increase. Likewise, the plunger being pushed down caused the pressure to increase, causing the marshmallow's volume to decrease. Plastic bag. The plastic bag floated into the air when it was filled with hot air from the hairdryer. This was due to Charles' law. When the temperature of the air in the plastic bag is increased due to the hairdryer, the plastic bag's volume increases as well, causing it to float. Soda can. The soda can expanded when heated by a flame and crumpled when placed in cold water. This was a demonstration of Gay-Lussac's law. When the temperature of the gas was increased by the flame, the pressure in the can increased. When the temperature of the gas decreased by cold water, the pressure in the can decreased as well,